Klömpner, the Dean of the Department, and I welcome you to this doctoral examination of Mr. Manuel Alexander Kretzer, speaking English because I understand the presentation will be in English, is that correct? Yes. I particularly welcome our two co-referents, namely Dr. Joakim Reuteler, Scope M, that's it, it must be you, and Professor Dr. Beesley, University of Waterloo, Cambridge, Canada. Welcome, thanks for joining us here. And obviously the Dr. Father, Professor Dr. Ludger, Hovestadt. I'm assuming you're familiar with the format. The examination takes altogether roughly about an hour. Half an hour is for your presentation, then there will be cross-questioning and examination, and we will retire for a moment to have a private conversation before we present you the result of your exam. The word is yours.
Yeah, thank you. Thank you all for coming. It's very nice to see so many familiar faces. Thanks to the committee. Thanks, Mr. Klömpner, for your time and availability. Thank you, Joakim, for providing great support, not only in respect to all the different materials, but also in helping me establish the structure and the order of my thesis. Thank you, Philip, for traveling so far, for being a great colleague and even better friend, and certainly an amazing inspiration of all these years since I've been working with you. And thank you, Ludger, for your unconditional and steady support, and for giving me the freedom and the space to do all which I'm going to present now. So, my thesis aims at describing emerging material phenomena and their potential for the creation of adaptive architectural environments, as well as a particular didactic model for their mediation within architectural education. These materials, which are often referred to as active or smart materials, are fundamentally distinct from the classical notion of materials, since they can transform their properties dynamically over a distinct period of time in a controlled manner and in response to an external impulse. Equally striking as their active properties, which can include shape change, color change, light emission, or electricity generation, and many more, is their purely synthetic constitution and their precise creation at a scale which has formerly been impossible. So these materials hence not only transport and transform information, but they're also based on information, being artificially designed from pure intellect. So in order to distinguish my approach from existing ones, I'm thus introducing the term information materials. With this I want to establish an awareness of a new materiality which has the potential to lead to profoundly different concepts in terms of architecture and spatial design. For the creation of dynamic architectural environments, these materials have various advantages over conventional technologies, which are still largely based on very basic mechanical principles. So systems that would usually consist of a multitude of interlinked rigid parts can, due to the holistic setup of these materials, be seriously simplified, reducing engineering complexity and potential hardware complications, lowering maintenance requirements and fabrication costs, making constructions much lighter and more slender, allowing to monitor and control a building's performance, and increasing its overall comfort and energy efficiency. Another highly interesting aspect of many of these active materials is their nonlinear actuation-transformation ratio, which we can experience, for example, in a thermochromic material. As you can see in this diagram here, the color change, which is induced by a change in temperature, is relatively slow in the beginning, then drastically speeds up and slows down again towards the end. While such a behavior is often regarded as a disadvantage due to a focus on precision control, I think that this very soft and almost organic phenomena again distinguishes information materials from the stiffness of mechanical systems and allows for a very intuitive and personal human association and acceptance. However, despite the growing interest in the performative aspects of this kind of materiality, most spatial scenarios are still rather traditional and fall far from exhibiting any of the distinct opportunities these materials offer. This has several reasons, I believe. Firstly, many of these materials are still technologically immature and often not developed in respect or with respect to architectural applications. And even if they are available as finished products, they have not only rather narrow properties, since they're always designed for a very specific purpose, but most likely also limitations in scale and durability, so they don't necessarily comply to building standards. Secondly, there is a big gap in between architecture and science. So the amount of information on new material developments which is communicated in a way that can be comprehended without having expert knowledge or insights is very constrained and often scientifically mystified. And lastly, and this is something that we as designers have to address, there is a lack in ideologically distinguishing information materials from traditional ones, which means that they're simply used to replace established technologies without questioning their suitability, and their defining dynamic properties are either constrained by forcing them onto existing structures or even neglected by standardizing and categorizing them to make them comparable to non-active materials and include them in existing databases and catalogs. So my hypothesis is that once we learn to overcome or to deal with these issues, information materials could enable the development of a technologized architecture where structure and skin could turn into unified interactive surfaces representing and being part of a person's hybrid identity, where materials could contain and carry information and energy to become active agents in networked ecologies, and where buildings could evolve from their primordial purpose of providing shelter, stability and safety towards more dynamic, responsive and possibly even alive environments. To approach this and to elevate these materials to become integral parts of spatial design, it will be essential for architects to actively engage in their development at an early stage. Truly interdisciplinary progress can, however, only happen if all involved parties share and communicate equal interest, and if they possess a general common knowledge of each other's area of expertise. Since current approaches towards information materials are either too general or conversely too specific for an architect's broad perspective, and certainly not valued enough in the present debate, I believe that new models are imperative. So the more immediate and less speculative aspect of this thesis is thus the assumption that the education of what I call an information material literacy will in the long run enable architects and designers to abstract and anticipate the functionality, behavior, and usage of any type of information material. Moreover, this knowledge will empower them to vitally communicate and collaborate across various disciplines and collectively drive the development of information materials for particular architectural applications. Since architecture, however, represents a highly diverse and complex discipline that is as influential on its environment as it is being influenced by it, predicting if and when such change will happen remains a matter of speculation. So hence, instead of making conjectures on the exact impact of information materials on architecture or trying to propose specific technical solutions or application, the main objective of this work is to promote a different kind of design and material thinking and mediate a more general awareness of the potential and meaning of information materials in an open and inspirational manner. This argument is structured around 5 interdependent and correlating sections. The first chapter of my thesis and the introduction to the thesis expands upon emerging technological, demographic, and socio-anthropological trends. It emphasizes the potential of adaptive spaces or buildings to address the quickly advancing nature of our environment, and highlights present tendencies but also shortcomings of applying information materials in architectural design. The second chapter is funded in the fact that the core of information materials, their inherently dynamic constitution, actually questions the very foundation of architecture, its stasis and permanence. So in order to gain a deeper understanding of the implications and possible effects of information materials, one thus has to reach further than only investigating the practical aspects, but has to explore the meaning of substance and materiality in a much more theoretical sense. So the main focus of this chapter is thus to provide a comprehensive analysis of the ever-changing notion of materials throughout history by looking at various architectural treatises and on how material culture has been understood and transferred within the respective context. Following a largely chronological order, the chapter is split into 5 parts: natural materials, industrial materials, and synthetic materials, which belong to the past, as well as digital materials and information materials, which represent the current state. Due to time constraints, I'm not going to expand upon this chapter. What can however be concluded is that the conception of materiality, but also very particular materials, has always been different, not only among varying times, cultures or societies, influenced by their availability, technology, or even fashion, but also from person to person. So speaking about materials objectively is therefore almost impossible, especially today where the amount of materials is much vaster than it ever has been. So the third chapter thus introduces an educational strategy which emphasizes the value of subjective physical prototyping and hands-on experimentation as being elementary for the acquisition of material knowledge. And it promotes the open and unrestricted access to this knowledge to foster its further progression and democratization from established structures. This is approached through 2 tightly connected methods. So first, I have run numerous material workshops and projects which throughout the past 5 years have steadily been refined and adapted. Throughout these courses, I usually try to engage in the very beginning with some specialists and scientists from the respective fields in order to develop practical instructions on how to self-make the chosen materials and then be able to teach the procedures to my students. After this initial introduction phase, the students are then encouraged to physically experience the functionality of the materials, comprehend their working principles, and understand the relation in between fabrication procedures and materials performance. And finally, they're asked to extract and emphasize a particularly exciting phenomena which they've discovered on the way. In parallel, they're asked to think about human or environmental situations or activities which could be enhanced through some kind of adaptive or responsive system. Throughout this part, the students are animated to think of spaces in terms of dynamic territories, considering architecture not as immobile and frozen objects, but as a series of events that constantly evolve and change over time. Finally, the 2 approaches, the bottom-up material exploration and the top-down situationist scenario, are brought together through a speculative spatial intervention. The relation to reality and presence is left open to the students, yet they have to express a certain architectural relevance and are intended to reach a scale which is more than just a collection of isolated prototypes or components. Hence, the main intention, at least for now, is not in developing finite products or proposals, but in providing the students with as little constraints as possible so they can freely explore and understand the materials, and in mediating an understanding of space and materiality as dynamic and fluid entities. Moreover, since I'm trying to avoid associating a particular material prematurely with a certain application, which I believe could potentially reduce its capabilities, the outcomes of these workshops should be evaluated by the vision they convey and the imaginative spectrum they enclose instead of their practicality. To, however, reveal the knowledge and the results that are gained during these courses to a larger audience and provide a basis of related research which could be taken further, I've initiated a second approach, which is the Materiality Research Network. This is a community platform, an educational framework, and an open materials database which provides in-depth access to emerging material developments. The website is divided into a publicly accessible area and a members-only section. The core content is split into 3 main categories. So first, there is a compilation of related physical projects and experiments which have been submitted, of course, by myself and my students, but also various other members of the network. Secondly, there are theoretical scientific essays on a growing number of information materials which describe the materials technically in terms of their history, their working principle, their fabrication and their usage. And third, there are illustrated step-by-step tutorials on how to self-produce these materials in an informal environment. Registration to the network is free and allows all members to unconditionally access all the provided information. Moreover, they can engage in forum discussions to receive more information and guidance on specific topics. They can represent themselves and their research interests. They can gain information on fellow members and their work and exchange with them via an internal messaging service. As of today, the network has exactly 1,118 active members. It is frequented by roughly 2,000 visitors each month from almost every country in the world. Most users stem from an academic and research-related fields, mainly from the areas of architecture, design, and engineering. More recently, however, due to the growing prominence of the network, interest from the industrial side has caught on, which in the future might help to develop some of these ideas towards more functional applications. The concluding assumption from these two approaches, so through the physical experience one gains when dealing with certain information materials and the potentially unlimited access to similarly comprehensive information on further materials, it will eventually become possible to develop a much more natural understanding and anticipate their functionality, behavior, and usage without necessarily requiring a physical working prototype. Just as one with a little experience in craftsmanship, for example, doesn't require to have or touch a piece of wood in order to know how it feels, how it looks, or what it can be used for. The fourth chapter expands upon this idea, being essentially an extension of the content described on the website. It represents a comprehensive evaluation of a selection of material phenomena, including aerogels, bioluminescence, bioplastics, dye-sensitized solar cells, electroluminescent displays, electroactive polymers, soft robotics, and thermochromics. Each material is described in terms of its historical development and purpose, its structure and operating principle, its fabrication process and common use, and its potential or speculative architectural application. For every part, the intelligibility of the theoretical research and the developed instructions are evaluated within a series of experimental spatial installations which have been realized throughout the earlier mentioned teaching modules and workshops. This format allows to link theory, material experiments, and environmental studies to a human-scale experiential situation. One of the earlier projects where we began exploring this approach was Phototropia, which was realized in 2012. Here the key topic or the key idea was autonomy. Autonomy not only in the sense that the designer, or we as the designer, become independent from commercially available or industrially prefabricated materials, but autonomy also in the sense to combine all these materials into a self-sufficient system which would create all the energy required by itself. The materials that we used all had in common that they were thin, rather flexible and lightweight, and that they could be produced following a set of rather simple instructions. So first we created electroactive polymers, which are dynamic elastomers that change their size or shape in response to a strong electrical field. So in principle, an electroactive polymer actuator is a compliant capacitor. So once a high DC voltage in the range of several kilovolts is applied, electrical charges move from one electrode, which are the gray parts in the diagram, to the other. As a result, the polymer film is squeezed in its thickness direction, which then leads to a planar film expansion. So the film becomes thinner and its surface area increases. And if this behavior is combined with a flexible frame that provides a certain stability, it can be used in order to create a three-dimensional movement, which you can see in these images here. The second material we used were electroluminescent displays, which are a type of flat panel display that emits a soft, perfectly homogeneous cold light, which is visible from great distance and essentially unlimited viewing angle. Electroluminescent displays are produced by sandwiching a light-emitting substance, which is usually a doped luminescent phosphor, in between two conductors. The front electrode obviously is or has to be transparent so the light can escape the system. They are very reliable with a lifetime of over 100,000 hours. They can be made in basically any color, are relatively inexpensive in production and require very little current. And finally we collaborated with scientists from the EPFL in Lausanne to produce dye-sensitized solar cells, which is a promising emerging technology and viable economical alternative to conventional silicon-based photovoltaic technologies. A dye-sensitized solar cell is a nanostructured photoelectrochemical device consisting of a highly porous film of titanium dioxide particles, which are coated with a monolayer of dye that is sensitive to visible light. So similar to the chlorophyll in plants, which produces chemical energy, this dye has the role of absorbing solar energy and then transforming it into electricity. So the effect is hence often dubbed synthetic photosynthesis. Dye-sensitized solar cells are made from relatively cheap and widely available materials through rather simple and inexpensive processes. They can be transparent or differently colored, and they exhibit high power conversion efficiency even under low diffused or indirect light conditions. So this means that they can basically also work indoors. As mentioned, the claim of this project was to produce all the materials in the installation ourselves. So the active components, which I've just explained, were merged and held together by a structural system made of bioplastic, which you can see in these struts here. They're made from bioplastic. After very after an initial phase of material exploration, we then began working very empirically on a number of tests on different solar cell shapes and sizes, and trying to figure out how many of them would be necessary in order to actuate all the other materials and how they could be combined together to create interesting and aesthetically appealing patterns and tessellations. The idea was then to create a rigid origami structure which would join all the elements together, elevated from the ground in order to create this kind of floating dynamic canopy. Initially the idea was to include all the materials into this fabric, also the electroactive polymers, so they were supposed to move and flex the structure. However, due to the fragility and the relative weakness of these components, they were eventually placed on the ground. And I have a short video which shows the project live. So this is the process of creating the electroluminescent displays. It's a screen printing process. Basically, you design a pattern, then you apply a luminescent phosphor, a dielectric layer and a conductive layer, and the EL display is finished. These are the electroactive polymers. Here we initially worked together with EMPA in Dübendorf, and they showed us how to make these materials. So it's an elastomeric material which is stretched, and then it's coated on both sides with a conductive powder, carbon powder. And then you apply 5 to, or depending on the size, 5 to 6,000 volts, and they start to move. Then we looked into different ways of making bioplastic. We then finally decided to use a gelatin-based recipe. The students were very explorative in trying different designs and opportunities. We weren't able to incorporate all of them, but it's a fairly durable material. And then we produced the dye-sensitized solar cells. This process is a little bit more complicated, but since we were closely working together with scientists in Lausanne, they were able to give us guidance and help us figure out the process. So these materials would then all merge together in this canopy. The solar cells were facing upwards in order to catch sunlight and create energy. The power was stored in batteries which were below the platform, and once these batteries were sufficiently charged, they would then start activating the active materials. We also had an infrared sensor which was basically checking the proximity or the proximity of people. So once it tracked somebody, and if the batteries were charged enough, the system would get active. Of course, all these components are very fragile, so after a week more than half of the installation had already died. But yeah, as I said, the focus is not on developing final products. The fifth and final chapter of my thesis summarizes it. It responds to the initially posed research questions, and it provides an outlook towards a softer, more sensual architecture of the future. In order to arrive there, which is of course purely hypothetical, I believe that we firstly have to do away with thinking in terms of limitations, be it scale, durability, affordance, or even resources, and instead understand constant technological progress as an opportunity which allows us to dare and to experiment, and which eventually will make any kind of development increasingly cheaper and more available. And secondly, I think we have to move beyond focusing purely on the functionality and the efficiency of these materials and the advantages they have over existing systems, but equally consider their emotive aspects and the more sublime impact they have on our senses. So engaging in possibilities and implications rather than the actual effect might hence be crucial in order to develop truly revolutionary spatial experiences and situations. Thank you.